linear algebra. And we have actually, you can buy it already. So there is, I will have one in the lab very soon. It's commercial. Okay, so one thing, and I want to mention very quickly one realization of Lighton where I was involved, which is probably interesting for you. But of course, I know very little of the math. This is a so-called direct feedback alignment, which is a way to train a network in a parallel way. So instead of doing backward propagation from the last layer to the first layer, what you can do in this case, you do some kind of parallel pass where you feedback the error to all the layers at once. And what you do is you use basically random weights. So this backward pass is done with random weights. So in a way, each of these is really a matrix multiplication with a random matrix. So we thought we could use that for training. And we did. And for that, on the optical machine, we had to basically modify a little bit the setup. I won't enter into the details, just to have some operation, some linear operation, because the problem is we have some nonlinearity at the end. That is the intensity detection. So we measure on the camera the intensity of the field. That is a modulus square. And for this particular operation, we wanted to get rid of this modulus square, which we did by some tricks. But the good thing is we could do it optically. And just to show you some very simple result on some very simple tasks. So on NIST and GraphConv, we could really, the back propagation would give you this kind of numbers. And if you do this the direct feedback alignment with optical ternarization, you get almost numbers which are in par with back propagation. Okay. So you can find some. Of course, we're trying to scale that up to bigger and deeper neural networks at Lighton. So I want to cover in the last, okay, maybe slightly more than 5 minutes, but what we did in terms of reservoir computing, that is another, this is something we did in my lab, not at Lighton, to use this random matrix multiplication for another tasks, which was to basically try to do this so-called reservoir computing framework. And reservoir computing framework is this recurrent neural network, and we know that they are very hard to train. So what was proposed by Jaeger and Haas in this paper was to fix all the weights randomly and only train the output layer. Okay. And this turned out to produce some decent results. And it was then, of course, very easy to train. But the nice point is if you have a reservoir, and what made the connection is if you make the reservoir fixed and random, well, each iteration of the state of the neural network is basically a random matrix multiplication. Okay, so you calculate the next step of the reservoir from some nonlinearity time some weights plus some input weights for the new input. Okay, so this is particularly well suited for physical implementation, and it has been implemented in many different domains, in particular in photonics, but not only. And I can point out this review paper if you're interested in the field. Okay, so how did we implement reservoir computing in our case? We have an optical setup that is basically what we do is we basically encode on the SLM the input that we want to train on and the reservoir states. Okay, then we go through the medium, and the medium will basically perform the matrix multiplication on both these things, and then apply a nonlinearity on the camera. So on the camera, we get the next step of the reservoir. And with a nonlinearity that is the modulus square because it's intensity detection. And then we do the feedback electronically. So we take whatever is on the camera and we put it back on the SLM electronically. So the matrix multiplication is optical, but the feedback is electronical. And then a posteriori, once you did all these steps for all the time series, you can do some training of this output weight to approximate whatever function you're training on. And this is typically not the bottleneck. It can be done on a CPU and a GPU at large scale. Yes?
So you have no feedback from the output to the reservoir?
It's electronic. It's only electronic. So we take the camera give you the state of the reservoir at some time. Yeah. And to go to the next step, you take electronically the image of the camera. You do some very simple processing like thresholding, and you put it back on the SLM.
No, I understand that when you train the output in the next slide,
yes.
You have a linear output.
Yes.
So but the output is not fed back onto
no.
the state. Okay.
No. Well, sorry, it is not for the training, but when we do some inference, what we can do is we can use this. Let me. We can use this inference to predict for longer the time series. So we don't let the system run with no input. We input to the network whatever the system predicts. Okay. So we use that for some time series prediction. So you can, for instance, so I don't probably need to introduce chaotic system here. So it's really this chaotic equation that behave, of course, very chaotically after a certain time. So the goal here is to predict the state of the system beyond a certain time, which is characteristic of the establishment of chaos, called Yapun of time. And we try two things. So one is this relatively simple one, which is the so-called Mackey-Glass equation. And something that is a bit more complicated is the so-called Kuramoto-Sivashinsky equation that is more similar to turbulence. So taking the Mackey-Glass equation, what we did was, taking some time series from this, then we feed that to the network. We train the output to the training series that we have, and then we use that to predict how the system will behave at subsequent time. And you can see that at least for some time we have some prediction, and then of course after some point, after some time it diverges in scale of the Yapun of time. So again we encode the reservoir state on the input on two parts of the SLM. We have a bias outside. This is the typical image we have on the camera, and you can see that the error of the prediction depends on the number of neurons. So when we increase the number of neurons, we get a better prediction. So this made us confident that since we could scale the number of neurons very much, that we could try a harder time series. And this 1D time series are used to benchmark this in most reservoir computing approach. But 2D time series is much harder. And this is what we got with 2D time series. So this is the ground truth. This is just the training part is before, but this is the ground truth of what we try to predict. This is the prediction, and when you do the error, you can see that you can get some decent prediction for quite some time. And we could actually show that the error as a function of time, this is for fixed reservoir size, and increasing the size of the time series. So how many spatial modes that we encode? Okay, so how complicated the time series is. And you can see that of course, the more complex the time series, the more difficult it is to predict. But if we now fix the time series to a certain spatial dimension, we can see that by increasing the number of neurons, we can improve the quality of the prediction to later time. Coming back to efficiency, so the nice point is the speed is independent of the time. So in electronics, you have this matrix multiplication. So you're in n square, where n is the number of neurons. In optics, it's almost independent. It's O of 1. Energy efficiency, we are about the same, so a little bit smaller, but it's typically the same. But it's not the optics part, it's all the overheads around it. One big part is the dimensionality, because electronics would tend to be very slow beyond a certain time as soon as you fill the memory for the matrix multiplication, while in our case, the in-memory computing, the memory is the medium itself, and we can go to much larger dimensions. So this is to show you, for instance, the time for one single iteration. And you can see that CPU and GPU, they really scale quadratically with a different prefactor, but they both scale quadratically, while the optics is almost flat. So that it's almost flat. There is a small overhead. This is the electronic feedback that is slowing down, but the optics itself is really flat. And you can see that beyond a few tens of thousands of neurons, optics is really much faster than the CPU or GPU. And beyond a certain dimension, of course, we can't compute with a single CPU or GPU just because of the memory problem. So in a way, we can say that beyond this point, we really have an optical advantage to do that with our machine. Okay, I'm at the end of my talk, and I just want to mention, and if I have a question, I can talk about what we did in terms of spin glass simulator with the same system. And we also have some work about doing some quantum state propagation in this system, and we believe that it has some potential for quantum computing, although this is very early, of course, and very proof of principle. But I just wanted to mention that we're also studying that. And with that, I'm at the end of my talk. I try to convince you that optical computing has some potential. It's very hard to do optical nonlinearities, but it has this advantage of scaling, multiplexing, and so on. Random projection is also something that you can use for reservoir computing at large scale, large dimensional. It's off-the-shelf component. You don't need, you basically benefit from what has been done in cameras and modulators. And of course, it comes with a problem of noise, how to encode the information properly on the SLM. You get a fixed random projection, so going beyond that is complicated. And of course, there's many ways to go beyond that. And one big important point would be to do a design matrix, of course, and this is, of course, very, very challenging. So the reason this works and even made it to a product is because it's so simple. Okay, so with that, I really want again to thank all my team, and in particular for the work on computing, this was a big involvement of Florent Zakala, and the two postdocs that worked on this PhD and postdoc are Jonathan Dong and Michel Raphaelian, who did all this work in particular on this reservoir computing work. Okay, thank you very much for your attention.
Are there any questions? Yes?
Yes, thank you for the great talk. In the feedback alignment work,
Yes.
so I have two questions. So you do the backward with your random projection.
Yes.
What are the forward ways? Are they also your metrics? Or are they
Okay. So I passed very quickly. And first, I need to say that this feedback alignment is something I was only marginally involved in. So, but I can really point you with the right people if you're interested to know more. But the key point is what we try to use is we try to use the optical machine to train a regular neural network, right? So the neural network itself that you try to train is not optical. It's you want to use the optical machine as a training machine for a neural network in your computer. Okay, so this deep neural network is fully electronic.
Question? Yes, Charles.
Thank you for the talk. Regarding the training, how do you calculate the updates in software?
So okay, so again, disclaimer. I was involved mostly in the optical part, and I don't claim to understand much So the idea is you take the error signal at the output and you feedback on the different layer, and this tells you somehow the rough direction in which you want to optimize to minimize your losses. So it's kind of a general gradient direction. But of course, it's not as precise as the backpropagation in giving you the right way in which to optimize. So it's a bit longer also to find the right to minimize your loss, right?
That's clear.
Yeah.
My question is different. How do you perform this calculation?
Yes.
In software, externally, like this is outside of the optical system,
Yes.
right?
The optical machine is just giving you
Just for
the how to change the weights.
So, like, if you need to, like, in terms of the vision, how do you see the backpropagation done? Like in an integration using optics, or doing it in electronics?
Well, the way we see it is, in principle, you could have in a data center where you try to do some training, you could have an OPU that would replace backpropagation, and that could very, very quickly compute those error signals to all the weights simultaneously for your GPU.
In any case, outside of the optical.
Yes. Yeah, absolutely. So you can just think of the optical machine as one way to get a matrix multiplication in O of 1.
So, follow-up question.
Yes.
The cost of the transition between the optics and the electronics, right?
Yes.
Because the question is, what is the real bottleneck here?
Yes. So indeed, so there is of course a cost to do the optic to electronic conversion. Actually, you have it twice. You have it at the encoding and at the decoding. So, but this cost is linear in basically the dimension of the input and the output, while the matrix multiplication is quadratic. Okay. So when you try to do things properly in terms of speed and energy, you realize that of course it's not worth it if you have, if you want to do a 1000 by 1000 matrix multiplication, the gain is not enough. But if you try to go to 1 million times 1 million, then it starts to make sense. Actually, it makes sense a lot, because the matrix itself is 10 to the 12 multiplication and accumulate. And then it's really worth to spend the energy to encode at the input and decode at the output. Okay, so
So that's, I think, a nice thing to discuss, because at the end,
Yes.
orders of
Yes.
magnitude. So
Yes.
maybe thinner versus quadratic, but the constants will be 5 orders of magnitude. So
Yes. So it's true. So what I can say that at least in the lab, we have been really doing low-dimensional stuff, and this has not been our concern. At Lighton, they did not the computation so much in terms of energy that in terms of speed. So really trying to compute the gain in doing this optical random projection rather versus regular random projection or other algorithm. And there is always a crossing points. I would say the crossing point is probably in the between 10,000 and 100,000 modes at which you start to be better. But it depends on the tasks. And I think also one point, and to me that's an important point, is even because of this problem of memory, sometimes it's not the energy that poses problem. It's really that at some point you need to distribute your calculation over many memories or do it in parallel, and that becomes a huge bottleneck. So yeah, it's but yeah, I would say Lighton has been trying to figure this out, and I would say also the one point is that I was showing you with this matrix of pixel and matrix of pixel on the camera and DMD, and I was always putting as the right number 1 million, which is the rough number of degrees of freedom, but it can actually be much bigger. For instance, you have cameras with 100 million pixels. So if you start to take these numbers, then it starts to be very important. Of course, you still have a problem of bandwidth, because if you have 100 megapixels that you read at 100 frames per second, then you still have a bus at some point that is problematic.
Apologize because I was so late. But sorry for the silly question, but do we really want to simulate backpropagation and all this? I mean, isn't it that kind of a wrong direction to go if one wants to be efficient? Because should we try to have a different algorithm, like some plasticity?
Well, so I'm definitely not the expert on that, but I would say that the nice point of this DFI is that it's parallel, of course. So it doesn't depend on the number of neurons and depend on the number of layers. So I guess it solves some of the issues of backpropagation. Whether this is the way to go, I honestly can't comment. I mean, some people say, there's some literature on DFR that claim it's some kind of biologically inspired. Whether it's better or different than other biologically inspired training like equilibrium propagation or others, I don't know. I honestly don't know. We're basically trying to explore all the possible use case of this random projection. So the DFA is one of them. It's definitely not the only one.
Okay, could you say just one more word about design matrix? You said I understand it can be very hard to do, but
yeah.
Can you just tell us maybe some perspectives about this?
Well, the problem is, okay, so first, I don't have a solution. I think it's a problem that we have in front of us for a long time. The problem is that, of course, the scattering process is extremely sensitive to the exact size of and position of all the scatterer. And of course, as you have multiple scattering process, light will basically bounce back and forth in the medium for a very long time. So if you have a medium that is highly scattering, the sensitivity is also exploding because it's like an interferometer, right? So you have what I mean is you have some kind of compromise to find between how complex, how dense, how random the matrix is, and how tunable it is. So what we have in mind, for instance, what at least I have in mind in my lab, is to say, okay, maybe what I could do is I could take a scattering medium, and I could, for instance, have some kind of layer that I could train on top of the medium. So I could have a random medium and then some kind of trainable layer in front of it that I could train optically or modify, tune a little bit this randomness. Making a fully designable dense matrix is to me not yet solved at all. So what I see is more as a way to tune a little bit the randomness in some direction, rather than doing a fully designed matrix. You can do it on a few layers that you cascade, like the terahertz work I was showing, but this is very difficult, and this has not been done in optics. And it's not very dense either. So
All right, thanks again.
Thank you.